Today we will continue with our journey in geometry. In the first part of this series, we talked about 5 ideas from geometry. In this one, we will talk about 5 more ideas, which can be very useful in contests like IOQM, RMO, and American math competitions. Let's get started. The first one is about the tangent chord theorem. The tangent chord theorem. So let's start by drawing a circle. And let's draw a tangent to the circle at a point. I'll draw a little bit better, I guess. I can draw a little better. So this is the point of tangency is A. And let's suppose this point is X. Let's take any point X on the tangent. And let's draw a chord AB from the point of tangency. From the point of tangency. That's important. So this angle right here, this is the angle XAB, which is basically the tangent to chord angle or chord to tangent angle. Right? The theorem says that this angle is equal to another angle which is made by the chord on the other side of the circle, alternate segment, which means you have the tangent chord angle on this side of the circle. So the chord makes another angle on the other side, and that is our chord angle. So let me draw it in green. It could be any angle actually, like this. A, B, C. So the claim is that angle XAB is equal to angle ACB. These two angles are equal. And the way to prove this, and I'll not give you the entire proof because we're just reviewing the ideas, but the way to prove this is very beautiful. You just start with the center of the circle. And this is a tip that I want to share with you, that whenever you are solving geometry problems related to a circle, make sure to mark the center and name it, even if it's not given in the statement of the problem. It is remarkable how useful the center of the circle is in every problem related to circles. So this is like a technique or a strategy or a trick, you can say. Alright, so now let's join AO and extend it to meet the circumference at some point, let's say D. So let's join BD. So the claim is that angle XAB is equal to angle ADB. Okay? XAB is equal to angle ADB. Now why is that? Well, if that is true, then we would be done. Why? Because remember, this is a very standard theorem in geometry of circles, that if you have any arc, then whatever angle that arc subtends on the circumference, they are all equal. All of these angles will be equal. If an angle is standing on this arc, standing on this arc means the endpoints of the two segments, they are on the arc. That we say this as this arc is subtending the angle. If the angle is standing on the same arc, then all of those angles are equal. This is a standard theorem in geometry, so we will be using that. So if we can show that this pink angle is equal to this one, then we would be done, because this one is equal to this one, by what I just said. So you can try to complete the proof from here, one thing to notice is that this angle is 90 degree because this is the angle subtended by the diameter, and in the circle is 90 degree. And this angle is 90 degree because this is the radius or the diameter and this is the tangent. So I want to talk to you about this second part a little bit more carefully. Notice that what I just said is diameter is perpendicular to the tangent at the point of tangency, right? So this is a very basic result in geometry. You can try to prove it, but to do that, you have to sort of think about perpendicularity a little bit differently. So there are two definitions of perpendicularity, and both of them are equal, the same definition. So the first definition is that two lines are perpendicular. They're perpendicular if this angle, if you measure the angle and it's 90 degree. That's when it's perpendicular. The second definition, and this is very important, that if this is the shortest path, so let's take this point as A and this line is L. If this is AD is the shortest path from A to L, the shortest path from A to L, then this is 90 degree or perpendicular. So there is one definition related to angle measurement. There is the other definition related to shortest paths. So there are two definitions. So here is the shortest path and here is the 90 degree. My challenge question to all of you is, can you show that these are equivalent, the same thing? Okay. So using this idea, you can show that diameter or radius is always perpendicular to the tangent at the point of tangency. And using that, you can finally prove the tangent chord theorem, which is one of the main tools in circle geometry. Okay. All right, let's move ahead with the theorems of Shiva and Menelaus. So these are very important theorems to prove that 3 points are collinear, that is, they stay on the same straight line, and 3 lines are concurrent, that is, they pass through the same point. 3 points pass through same line, and 3 lines pass through same point. These are, in this sense, these are like dual theorems. Dual theorems. In fact, one can have a very interesting discussion about the duality of Shiva's theorem and Menelaus' theorem in the context of something called projective geometry, which we cannot discuss here today. It's a very, very beautiful discussion. Notice that in these 2 lines, if I exchange the word point by line, I get the other statement. If I replace point by line and line by point, I get the other statement. That's why it's called a dual theorem. Okay? And this duality is presented everywhere in mathematics. It is in platonic solids, the 3D geometry. It's in this particular domain of planar geometry. There are many areas where duality is. In higher mathematics, there is something called Poker duality, which is very exciting. Homology and cohomology groups are in some sense dual. So you can go on and go on forever. But in this particular case today, I just wanted to share with you the statement of Shiva's theorem. So basically, if ABC is a triangle and AD is a Shavian means a line segment joining a vertex with a point on the opposite side. It's a Shavian. Similarly, BE is a Shavian and CF is a Shavian. And they all pass through the same point T. Then, if the lines pass through a single point, then we can say that BD over DC times CE over EA times AF over FB is equal to 1. Notice how I did this. I started from BD over DC, CE over EA, EAF over FB. That product is equal to 1. I'm not going to prove this today, but this is a very, very powerful theorem. In fact, the converse of it is also true. The converse means if you have a triangle ABC, suppose you have not drawn the Shavians, you have just the triangle ABC, and you have 3 points D, E, F on the 3 sides of the triangle, and it is known that BD over DC times CE over EA times AF over FB is equal to 1. Suppose that's known. Then you can say that AD, BE and CF then pass through the same straight line. So it goes both ways. Think about it. If they pass through the same point, then the ratio is multiplied to 1. If the ratio is multiplied to 1, then they pass through the same point. So I think this goes both ways. Same thing happens with this Menelau's theorem. So let me quickly tell you the Menelau's theorem. So the Menelau's theorem is like this, that if you have a line and if you have a triangle, let's extend one side of the triangle, A, B, C, D, and if you have a transversal, that is a line cutting the 3 sides. It cuts AB internally, it cuts AC internally, but it cuts BC external, is extended BC. Okay. Let's call this X, Y, Z. Then BX over XC, BX over XC times CY over YA times AZ over ZB is equal to 1. Actually, if you use erected line segments, then we can say it's equal to -1. But let's not go into that computation. Just the magnitude-wise, if you just divide and multiply, you will get 1. And again, the converse of this is also true. So if you have a triangle with one side extended, if you have 3 points and this ratio is satisfied, this product of ratios is equal to 1, then those 3 points will be on the same straight line. Okay, so that's the Menelau's theorem and its converse. It's very important. Now let's go ahead and talk about the next idea, which is the third idea for today, 8th idea in total. This is the power of a point idea. So you have a circle, you have a point P, and you ask, how do we measure the distance of the point from the circle? How do we measure the distance of the point from the circle? So what you do is you draw a tangent. Let me draw it carefully. You draw a tangent. Let's call this T. And you would also draw a secant in, suppose. Then you can say that the distance of the point P from the circle is pt squared. That's the square of the tangent, which turns out to be equal to PA times PB. So this value pt square or PA times PB, this is called the power of the point P. Power of the point P. Power of the point P. Okay. This is very important. Many problems in geometry can be solved using the notion of power of a point. In fact, there is an associated idea called radical axis, which basically says that if you have two circles, let's say one of them is like this, one of them is like this, then find all those points whose power is same corresponding to these two circles. So if P is a point with that particular property, then Pt1 square then be equal to Pt2 square. Pt1 square is equal to Pt2 square. That's how power of points. So the radical axis is defined. That is, you take all the points in this property. It turns out that this will be just a straight line perpendicular to the line joining the centers of the two circles. But be very careful. The radical axis, which is this line, may not bisect the line joining the centers. In fact, in most cases, it will not bisect the line joining the centers. So that's what power of point is. Let's go into the notion of cyclic quadrilaterals. So how do you identify that in a circle, how do you identify that a quadrilateral is cyclic? That is, how do you tell that four vertices of the quadrilateral lie on the same straight line? Say A, B, C, D. So one way to do this is that you add the opposite angles. Let's say angle A and angle C. You add the opposite angles and you get 180 degree. If that happens, then it's cyclic quadrilateral. In fact, there is a slightly modified corollary of this. If these two angles are equal, that is, one exterior angle is equal to opposite interior angle, then the quadrilateral is cyclic again. Okay? There are a variety of ways to prove that a quadrilateral is cyclic. I'll give you one interesting way. It's called the Tolenis theorem. It basically says that suppose you have a quadrilateral, let's say A, B, C, D, and you join the opposite sides of the quadrilateral like so. Then, now by the diagonals, that AB times CD, that is the opposite sides multiplied, plus AB times BC, another pair of opposite sides multiplied. If it's equal to AC times BD, then this quadrilateral is cyclic. Then this quadrilateral is cyclic. Cyclic means all the four corners lie on the same side. There is a very important relation of this with the case where it's not cyclic. what happens if it's not cyclic? Okay. But there is another case where there is a curvature of the surface, and this we discuss in our research programs at Chinta. Sometimes, if the curvature is negative, then something weird happens in this Ptolemy relation. Okay? It's sometimes called the 4-point relation. I'm just giving you a hint. You can Google it or try to find it somewhere, the 4-point relation in the negative curvature surface. Something weird happens there. But in the comment section, you can tell me what happens if we are on the plane, Euclidean plane, and this is not a cyclic quadrilateral. In general, what would happen? Okay? So in the final point, we will talk about the Fermat-Cohen problem. The Fermat-Cohen problem is very simple and beautiful, that if you have ABC a triangle, can you find the point P such that PA plus PB plus PC is minimal? Minimal means if you take another point Q and find QA plus QB plus QC, then that sum will be greater than or equal to PA plus PB plus PC. So PA plus PB plus PC is the smallest possible value of this sum. This is an optimization problem in some sense. If you are supposed to build a computed hub, and if you want the wire lengths to 3 volts to be minimal, if you want the wire lengths to the 3 ohms to be minimal, then you would want to find this particular point. So how do you do it? Well, I'll give you a hint, and you have to show that this is true in the comment section. So what you do is you draw equilateral triangles on 3 sides of the given triangle. Okay? You draw equilateral triangles on the 3 sides, and you join the vertices like so. It will turn out, and this requires a proof, it will turn out that they all pass through the same point. And that point, my friend, is the desired Fermat point, which is having this particular plot. So I want you to show this in the comment section. This can be done in a variety of ways. It can be done using synthetic geometry. It can be done using rotation. It can be done using complex number and geometry, which is a very beautiful subject on its own right. Give it a try, put it in the comment section, and I hope you like this kind of review videos. I will come back with more such videos in the upcoming days. Thank you, and goodbye.